We're going to spend another day with velocity and acceleration, and we will call this day 2. And if you are taking notes at home, we are now on worksheet 2, or module 2 in the packet that we're working through. And if we look at example 1, it says the data in the table below gives selected values for the velocity in meters per minute of a particle moving along the x-axis. So these are velocity values. All right? And so on this table, which I'm actually going to put up here so I can draw on it, time 0, the velocity is -3. Time 2, the velocity is 2, 5, 3, 6, 5, 8, 7, 12, 5. Okay? So, at time 0, let's look at our first question. And we're working through the worksheet, so if you're taking notes at home, just follow along with that. At time 0, which way is the particle moving? At time 0, remember these are velocity values. So at time 0, the velocity is negative, which means it's moving to the left. Okay? Remember, velocity gives us both speed and direction. All right? Question number 2. Is there a time during the time interval from 0 to 12 minutes when the particle is at rest? And explain your answer. Yes. Very good. Yes, there is. Why? It changes direction. How do I know that it changes direction? The signs change. Because the sign of the velocity changes. All right? It changes direction because velocity changes sign. If we look up at my table, at time 0, it has a velocity of -3. At time 2, it has a velocity of +2. So somewhere in between there, the particle had to be at rest. All right? Had to be. Okay? Now, that is technically, by the way, what theorem did we use with that to come up to that conclusion? I need to kind of refresh your memory about a theorem we've covered. And that is the intermediate value theorem. And, you know, as somebody who's been an AP reader, I can tell you that sometimes they're looking for some justification like that. It is the intermediate value theorem that says it had to be 0 at some point. Now let me kind of explain the intermediate value theorem, how it relates to this problem again. All right? Let's look up at these two values again, here and here. Let's consider a graph for a second. If the value of the velocity at time 0 is -3, here's -3. Now remember, this is time, and the y-axis is velocity. Remember that. Okay? This is important. At time 0, the velocity is -3. All right? At time 2, the velocity is 2. So at time 2, the velocity is now 2. The intermediate value theorem says that a function takes on all of the values in between. So in other words, if the velocity goes from -3 and whatever it does, it winds up at 2, the intermediate value theorem says it takes on all of the values in between -3 and 2. So at some point, it had to be 0. all right, if the function is continuous, all right? So, and by the way, we were told that the velocity is a differentiable function, all right? So that means that, it is continuous. The intermediate, this is the explanation of the IMV, the intermediate value theorem. I guess, sorry, IVT, intermediate value theorem, okay? It assumes all of the values in between -3 and 2, which is how we know for sure that at some point the particle changed direction, all right? All right, finally, we're ready to go on to question 3 now. Question 3. Use data from the table to find an approximation for v prime of 10. Let's stop right now, because one of the things you've got to learn how to do is recognize key words. As soon as you see approximation, that's a key word, all right? It did not say exact. It said approximation. And then I'll explain that in a minute. Find an approximation for v prime of 10. And explain the meaning of v prime of 10 in terms of the motion of the particle. Show the computations that lead to your answer and indicate units of measure. Now, doesn't this say find the derivative of velocity? So it is the acceleration, but before we get to that, what is derivative? What is the derivative of something? It's slope, right? So we're thinking slope. All right? Now it said to do it from the values of the table. Let's go back to the table for a second. Well, lo and behold, I don't have anything for 10, do I? But I do have values for 8 and for 12. And do you remember the key word I just said? Approximately. So don't I have 2 points? Right? Yeah. So can't I approximately find out what the slope is at 10 using those 2 points? Let's do that using these 2 points right here, 8, 7, and 12, 5. So I have 2 points, 8, 7, and 12, 5. And yes, it's back to our song again. Slope equals, in this case, it's change in velocity over change in time, but that doesn't matter too much. We're still just going to do slope. So it's going to be 7 minus 5 over 8 minus 12. Okay? Did I get my points correct? 8, 7, and 12, 5. Yes, I did. All right. So what I wind up with is 2 over -4, which is -1/2. Now, somebody said a minute ago that that's the approximate acceleration of the particle, right? What else can I say? Did it ask for anything else? Oh, no, it just said to calculate, explain the meaning of v prime of 10. Well, explaining the meaning is that this is acceleration. Okay, and that's enough for number 3. Let's go to number 4. Let a of t denote the acceleration of the particle at time t. Is there guaranteed to be a time t equals c in the interval, so we're looking at the interval 0 to 12, is there a time such that a of c equals 0, and justify your answer? So, how can we do this? Is there a point in between so that the acceleration of a certain value is 0? If a particle is at rest, then yes, that is correct. But we could also say if the velocity is constant, right? If because remember, acceleration is the derivative of velocity. So if I have a constant function, right? If the velocity stayed at a constant value, then we could also say that the acceleration is equal to 0, right? So let's go back to my table, okay? Now remember, we were given velocity values, and I know my table's getting messy here, but that's okay. If you look at the velocity, we can see that we start at -3, right? We go up to 2. Now, so isn't the velocity increasing at this point? Yeah. Increasing, 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 decreasing. Now, so if we're talking about velocity values, okay, and this is a good place to kind of come back to my intermediate value theorem graph. -3 at time 2, it was up to 2. If I continue this graph, it's going to keep going up, okay? Let's see, at time 8, it was up to 7. Okay, so when I get over to 8, this thing was up to 7. But then, at time 12, it's down to 5. It's down here someplace at 5. Now, acceleration is the derivative of velocity. So it looks to me like if I were to look at the slope, there has to be a place, all right, where the slope was 0. And guess what? That is still using the intermediate value theorem. There had to be a place, all right, where if the velocity changes from positive to negative, okay, it's just like what we said before, you know, I know that a particle's at rest if the velocity changes sign. Well, here I know that there has to be a place where the acceleration is equal to 0, okay? A of c is equal to 0, again, by the intermediate value theorem, because the velocity went from increasing to decreasing. There had to be a place where it was equal to 0. Okay? All right, now we're going to look at example 2, okay, which is in your handout. I'm going to draw a sketch of it so that we can see it. We've got this sketch that does this, this, and this. And we're told that this is 3, this is 12, 1, 2, 3, 4, this is 5, this thing is 3, this is 6. Okay? We have a graph given to us that represents the velocity. This is v of t, the velocity function, not the position function. This is the velocity function. The question under example 2 says, at t equals 4, is the particle moving to the right or to the left? Now, the graph below, this is velocity. Okay, these are the possible velocity values. So it's very important to note that this is a positive velocity value. Isn't this also a positive velocity value? Yeah. Now, it would have a negative slope, but we're not concerned about that right now. We just want to know, is the velocity positive or negative at time t equals 4? And at t equals 4, I'm answering question 1 under example 2. At t equals 4, the velocity is positive, which means that it's moving to the what? To the right. The particle is moving to the right. Okay, this is very common AP Calculus type questions about velocity. Question number 2. Over what time interval is the particle moving to the left? From 5 to, and now on your graph, doesn't it stop at 9? 6, 7, 8, 9. Okay. Okay, so it is moving to the left when t is in between 5 and 9. Okay? Now, wait, I shouldn't have that greater than or equal to there. It should just be greater than. And clear up and including 9. It is moving to the left. Why? Because down here it has negative velocity values. So if it has negative velocity values, it has to be moving to the left. Okay? Question number 3. Trying to squeeze these in on this page while I can see my graph. At t equals 4 seconds, is the acceleration of the particle positive or negative?
No, go down the river graph.
All we need to know is the acceleration positive or negative when the time, remember this is the time axis, when the time is 4. So all I need to know is, what's the slope of the tangent line right here? Negative. Okay? The slope is negative, so the acceleration is also negative. Okay? Remember, acceleration is the derivative of velocity. Okay? Question number 4. And I think I will have to go to a new page now. Question number 4. What is the average, there's one of those key words again. It did not say instantaneous. It said average acceleration of the particle over the interval from 2 to 4. Show the computations that lead to your answer and indicate units of measure. All right? So, average acceleration is going to be just change in distance over change in velocity over change in time. Okay? It's going to be change in velocity over change in time from 2 to 4. Okay? So, all I need to do then is find v of 4 minus v of 2 all over 4 minus 2. And we can calculate, we can find all those values from our graph. Now my graph isn't as good as yours, but I can see that v of 4 is 6. Yes. v of 4 is 6. v of 2 is 9. And then I have 4 minus 2. All right? So you have negative 3/2. That is my numerical answer, but didn't it say that we needed a unit? Well, acceleration would be feet per second squared. Okay, and that's something that's convenient from physics. Question number 5. Is there guaranteed to be a time t in the interval 2 to 4 such that v prime of t equals negative 3/2? I'm wanting to know can I be guaranteed that v prime of t, which remember is the acceleration, is there a place where it's equal to this value that we just got? Are we guaranteed that? And the answer is no. And one reason is because of the graph. Don't I have something up here that's not differentiable? At that place, it is not differentiable. All right? So we are not able to guarantee that because of that point. All right? Number 6. Get my pages straight here. Yeah, there's a point that is not differentiable. All right? We have to, if you think about a secant line, okay, over here was 2. Okay? We have to be able to think, here's 2, here's 4. Remember what a secant line is. This is a secant line, right? This secant line has to, at some point, you know, if these points come up like this, whatever, there has to be a place where it winds up being -3/2. Well, the problem is, when I get up here, I can't describe that. Okay? Let's look at question number 6. At what time t in the given interval is the particle farthest to the right? Well, this is a good question. At what time t is the particle farthest to the right?
T equals 3. Oh, wait, no, 3. Because the other one down there is on the left.
Now, let's remember something.
5.
I am hearing a couple correct answers. The answer is 5. And let's think about why. Because for all of this, let me get a new color. For this entire time frame from 0 to 5, the particle has a positive velocity, which means it's moving to the right from 0 clear up to 5. At no point was it moving to the left. From 0 to 5, it was moving right. Okay? At time 5, we started having negative velocity values, which means it started moving back to the left. And it moved to the left the rest of the time. All right? So I know from 0 to 5, it was moving right the entire time. It was farthest to the right at time t equals 5. Okay? And we are going to stop there for today.